Welcome everyone to my presentation. My name is Sultan Al-Owais. I am participating in this conference in a personal capacity, not representing my employer, and I'm speaking for almost 15 years of experience with cybersecurity in many critical infrastructure fields. In my previous experience, I've worked for industry, telecoms, and nuclear power, and I believe I've gained a lot. In this presentation, I'll be trying to summarize a lot of that by beginning to ask what is, in the view of the audience, critical infrastructure. Critical infrastructure is assets considered essential for the functioning of society and the economy by governments. That typically includes power, water, food, healthcare, communications, manufacturing, defense, law enforcement, and other essential industries. Critical infrastructure is usually very, very high in value and therefore low in flexibility. Where information security is about securing information, operational security is about securing operations, often from the security guys. The field of critical infrastructure and operations is very often adversarial to methods to improve it. There are many false or misleading trade-offs in the considerations of cybersecurity and critical infrastructure. Security is often seen as detrimental to safety or detrimental to utility and the ability of the operators to do what they need to at the right time. The security of critical infrastructure matters to hackers, besides the obvious, which is either that they're trying to hack it or someone hacks it and stops them from thereby from hacking someone else. It matters in that information systems today are no longer just information systems. Digital transformation is not something that an organization or an entity does. It's an economic necessity. It's something that's happening to us, not something that we are participating in. It is no longer economically viable for any entity to ignore the efficiencies that can be gained by modernization, which means modernization is spreading and pervading everything in our lives. Although real life matters and not everything will become digital, it's very interesting to consider what will happen as we approach more and more digitization in our daily lives. And it's very informative to start considering that there is almost no information that's not digital information today in our daily lives and our daily interactions. And very soon we can consider that there will almost be no crime that's not computer crime in one way or another. To define the problem, I define cyber, and this is my personal definition that I don't know if someone else adopts, but to me, cyber is the protection against unintended consequences to an engineered system through adversarial action. Security of industrial systems and critical infrastructure lags definitionally behind the state of the art. There's high investment. There are longer-lived systems. There are longer engineering cycles, test cycles. There is more burden of proof necessary to certify that equipment is safe to operate. And organizations that build a power plant spending millions are unlikely to reinvest after it's done because they think it's done. Operational technology generally and hopefully is more difficult to reach and is isolated to some degree. Therefore, harder to exploit. It's not saying that it's always harder, it's just saying that unless you really, really make big mistakes, your operating equipment is not pingable from the internet and is not sitting on an unprotected web server, we hope. Motivated adversaries must direct more efforts into subverting insiders that work at an isolated facility or an air-gapped facility They must direct effort into gaining control through unintended control paths or into subverting the supply chain to get compromised assets or compromised software into a facility. There are many examples in recent history. Many of the audience will be familiar with them. I don't believe I have the time to go through any. But we have to remember that with higher value targets and a higher cost of entry, one is likely to get more highly capable and resourced attackers. Problem definition continued, or why perfect security is impossible. There are two ways to think about security. One of them is an integrity model where what you have is perfect and you don't want anyone from outside messing with it, so you don't allow any information in. The other model is where you don't care who changes what you have. The confidentiality model means that what you want to do is protect your secrets and not let anything out. Quite obviously, perfect security is the combination of both, and where you combine both, you no longer have an active system. You have a computer that is shut off and inaccessible. Security and safety, especially in industrial systems, are complementary despite the concerns of those primarily involved with safety. They are both aspects of a larger set, which is reliability. Where safety is the protection against accident and unintended consequences, security is always the protection against an adversary. And security is adversarial. Sentient adversaries, intelligent people exist and will find ways around your defenses. What makes that tougher to deal with is how complex and how pervasive technology is. We can barely understand the technology that we use. Instead, we abstract it, and then we believe our abstraction. Tech matters a lot and more as time goes on. Information systems today are full of exploitable weaknesses, often that we don't know about or don't understand or cannot fix because we cannot disrupt running systems, especially in industrial environments. And the model of security in an industrial environment is usually a multi-layered defense model where you just have more and more layers of the onion, where integrity comes first, where information is only allowed out from your most critical systems, and your less critical systems can have bidirectional communication, and the supposition is that only authorized personnel with suitable training in a controlled area can make authorized changes in accordance to a procedure. This is only a model. Because industrial design prioritizes safety with redundant communication paths and direct connections and multi-homed machines, there's gaps in this. The diagram looks very reassuring, but it is almost never like this. And if it is like this, it's only like this with exceptions. Even then, skew occurs, changes are made. The security of a system deteriorates to the point that the system is most secure the day it's commissioned and starts going downhill from there. A model that's not uniformly enforced is therefore only partially and only locally effective. And then there's digital transformation and all the economic drivers for people to connect everything to everything else, which makes us rethink this model. This model, seen as a diagram, makes us think of 3D reality. Feet, shoes, people running, guns, gates, guards. But cyber reality or electronic reality is a little bit different. For one thing, observation of cyber action is harder than physical action. Action is non-obvious. It's asymmetrical, complicated. The technology is counterintuitive. It's abstracted and multi-layered. Security monitoring is also typically best effort, meaning that we do the best that we can and then we call it excellent, but we stop there. It's slow to develop and implement, it's disruptive, and it lags behind the attacker. Unique identification of actors in similar environments is not common and it's not simple. In factories all over the world, there are shared accounts because people prefer to be able to reliably get into an engineering workstation when they need to. That's why the password is typically engineered. Don't tell anybody I told you that. Engineering teams have a justified safety bias and a bias towards conservative decision-making. And lastly, security measures done wrong can often introduce weaknesses. Imagine in a system where you depend on isolation for security, that you put in an authentication server that can be reached from everywhere and a log collector that can be reached from everywhere. Those become potential vulnerabilities in your system because you, in order to enable them, you disable the isolation that used to be part of your defensive strategy. Cyber can gain from physical security in many ways. Many of the controls that are traditional to physical security are very useful, such as personnel security programs, fitness for duty programs, perimeter security, and physical access control to facilities that prevent people from coming in with a USB, plugging it in, and owning your entire network. But cyber has its own flavor because of the asymmetrical impact, the non-obvious harm that can be induced, and the complexity and non-intuitiveness of computerized systems. What I'd suggest is high priority controls for industrial environments. Start with focusing on non-repudiation. If you have so much into the invested in the unique identification and tracking of individual actors, potential insider threats, then shared passwords and non-logged events don't help you. Computer actions must be uniquely linked to an identifiable actor. Single actor behaviors must be linked to actions and changes across different security levels, and I would strongly recommend a PKI-based system where shared nothing authentication becomes possible. Second, application whitelisting is an indispensable tool. Blocking a virus or waiting for patches to be applied when you don't know what attack and what payload are going to come at you are not enough. By default, everything should be distrusted. All the applications that could be run should be distrusted, and only those that have passed rigorous testing and validation should be allowed. And this should work in an industrial facility in line with the facility's industrial change management procedure. Passive monitoring of networks becomes essential because chatter in industrial networks is very often detrimental. And statistical monitoring of network behavior and user entity behavior become very, very useful tools the more if we allow them to grow organically. If we, however, try to impose them by force, these programs typically fail. I'm sorry for zooming through the presentation so fast, but just in the interest of time. What I'd recommend to all security practitioners, industrial or otherwise, is understanding first what success means at cybersecurity, because it's undefined. It's impossible to become perfectly secure or reliably prevent your organization from getting hacked. It's impossible to prove the value of your efforts, to prove or assume that you're not hacked already, or demonstrate that you did a good job when you do get hacked, or when you don't get hacked, or when you get hacked and don't know about it. In lieu of that, I believe a useful target is seeking to become better constantly and gradually at monitoring, response, defense, documentation, organizational transparency, finding solutions, meeting demand and delivering answers, better at architecture, better at design, and better at reuse. Continuous improvement is not only the result of an annual audit cycle or a regulatory compliance audit. Those are too slow. Continuous improvement to be effective in an organization will need to be continuous. What is strategy? But a pattern in a stream of decisions. Vision or mission statements like wanting to become a center of excellence or building a SOC to deter and detect something, or repeating platitudes like the confidentiality and integrity and availability doesn't really add value and doesn't define what you're actually going to do. In my experience, the organizations that succeed at making their security better day by day are the ones that assume responsibility for cybersecurity. How do they do that? They accept and improve on what they would have opposed. They pursue what they need, whether it's buy-in, whether it's trust, whether it's organizational maturity. If you need it to happen, you go make it happen. They prioritize process because people don't make technology better. Technology doesn't make process better. It's process that makes people and technology better as time goes on. Successful teams integrate constantly. Where they have equipment and technologies that are not fully leveraged, they have no business buying and investing in something else that will make the problem worse and not better. They simplify constantly. They prioritize things that offer the most residual value, and they deprioritize measures that are premature but sound good. Successful teams distrust generalities, decisions made on principle, and technology silver bullets, and they own decisions and base them on pragmatic, longer-term considerations. Summary of industrial recommendations and overall recommendations is that the safety, the integrity and availability of systems is the overriding concern in critical infrastructure, and for very good reason. Security done right only supports and promotes safety. Industrial environments are unique to themselves. The challenges of each environment are unique and different to the challenges of every other, and cannot be generalized. Legislation and best practices do not generally apply across different industries and across different facilities. If you're counting on regulation or vendors or auditors to save you, you're already in trouble. Before implementing technology then, organizations that take responsibility for their security set themselves up to succeed. Mindful and well-considered prioritization is indispensable, and as W.E. Deming said, there is no quick fix, there is no instant pudding. Thank you all for listening.